Hello, this is Burak Boyacıoğlu from Turkey, Istanbul Technical University. Due to the emerging situation in Turkey, I'm joining you via this video. Our paper with Şeniz Ertugrul is about motion planning of manipulators by using the algorithm RRT. The suggested method focuses on the manipulators and it uses rapidly exploring randomized tree algorithm which avoids obstacles, but the path given by RRT is jerky, so it needs a post-processing. In other words, it needs smoothing, and we prefer cubic splines as suggested by Lean and his friends. We also time optimized the cubic splines by using Nelder-Mead method. Sampling-based planning approaches, there are lots of them, but randomized potential fields, probabilistic roadmap method, and rapidly exploring randomized tree are very popular, and there are some versions of them. You can see an application of RRT on a humanoid robot arm by Perez and his friends at MIT. I want to briefly talk about rapidly exploring randomized tree algorithm. Here is the pseudocode for the RRT. At the beginning you have the initial configuration and the goal configuration, and you sample in the sampling space, in the planning space, and if the sample is close enough to the initial configuration, you directly connect them. Otherwise, you draw a line from initial configuration through the random configuration with an epsilon length. The tree grows like that, and when it reaches the goal configuration, it stops. You will have the connectivity path. It is continuous, but it is jerky. So you will need some smoothing. There are more than one subfunctions of sampling-based motion planning algorithms. For example, you should define the metric, the nearest neighbor algorithm, the local planner, the collision checker. How do you select the parents? How do you sample? For local planning, there are many options. For example, you can use B-splines or cubic splines. But while you are using B-splines, you should define control points, which bases on heuristics. On the other hand, cubic splines doesn't require that. So we prefer cubic splines as suggested by Lean and his friends. If your acceleration function is linear, the velocity function will be quadratic and your position function will be cubic. So they are all continuous functions. Here, there is a pseudocode of Nelder-Mead algorithm. For a cost function with n variables, you should define n plus 1 possible solutions. Then you will replace those solutions with better solutions until you will obtain the optimal solution. It is a search algorithm. In our case, the cost function is the total time. In other words, the summation of time intervals, h's. If you have n minus 1 time intervals, you will need n possible solutions. There is a methodology for these possible solutions. We define xi commas. If they are not feasible, we convert them to their feasible versions. For the approach, we suggested the initial configuration and the desired position in the task space are known. In each step, we transfer the tree from the configuration space to the task space, so we need forward kinematics, but not inverse kinematics. We also know the velocity, acceleration, and jerk constraints, and positions and sizes of the obstacles. This can be known by a camera or another learning tool. Here our case study. I take humanoid robot arm. You can see the DH parameters. There are 6 revolute joints of this arm. We use Maxon motors and harmonic drives in each joint. For this scenario, we define 4 spherical obstacles. Here is the initial configuration and the desired pose. We use configuration space as the planning space, Euclidean distance as the distance metric. You can see the tolerances for the goal position and the goal orientation. The connectivity path we have obtained is given in the table. It is a solution, but it is not the only solution. It is one of infinite amount of solutions. So it is not the ideal solution. Here kinematic constraints for smoothing, and after curve fitting and optimization, we obtain the total time as 2.6 seconds. Here is the vector of time intervals, and here are the characteristics of position, velocity, and the acceleration. They are all continuous. You can see the motion, the connectivity pad, and the curve we fitted. Here, the blue area is the goal area with a tolerance, and there are 15 frames from the motion. In this paper, we combined 2 methods and planned the trajectory without using inverse kinematics. We explicitly explained the smoothing process of the RRT-given path, which is not always done in RRT papers. We also considered jerk constraints which is not common. Time optimization is done for cubic polynomial joint trajectories based on RRT-given path. For the future work, we plan to adapt our approach to other sampling-based methods and other versions of RRT, such as RRT star and dynamic RRT. Line of sight algorithms may be called to shorten the connectivity path. Finally, we plan to test our results on the real system, which is in the assembly phase. Thank you for listening.